So today we're going to talk about a serious chemical glow-up. It's a story all about how scientists cooked up a brilliant new recipe for molecules that are, well, kind of essential for everything, from the drugs that keep us healthy to the very screen you're looking at right now.
It's a fantastic question, right? And the answer is a tiny but absolutely mighty molecule. And the story of how chemists finally figured out how to build it efficiently, well, it's a story of pure elegance and innovation, with some seriously bright results.
All right, let's meet the hero of our story, the thiophene. It's this special kind of molecule with a sulfur atom tucked inside. And it turns out these little guys are the unsung workhorses behind some of our coolest, most advanced tech. I mean, their versatility is just incredible. Think about it. They're the core backbone of more than 200 different FDA-approved drugs. They're also a huge reason your phone or TV screen has such rich, vibrant colors. Yep, they're in those OLEDs. And because they can fluoresce, glow, they're perfect for everything from lighting up cells in medical imaging to even detecting explosives.
So you'd think, if these things are so important, we'd have a really slick way to make them, right? Well, for a long time, not really. The old-school methods were clunky and messy. We're talking multiple steps, lots of unwanted byproducts, and pretty harsh conditions. The holy grail for chemists was to find a simple, clean way to build them in a single step, in one pot, using really common ingredients.
And that right there brings us to the breakthrough. A team of researchers developed an amazingly efficient new method. It's a three-component reaction that's just as elegant as it is powerful. So let's meet the cast of characters.
Okay, so the recipe starts with three pretty simple ingredients. You've got two common carbon-based molecules, an aryl ketone and an activated alkyne. But the third one, it's just simple elemental sulfur, literally the raw element, which naturally exists in this cool ring shape. The whole goal is to get these three to come together in one single pot and form a totally new molecule.
But, for any chemical party to really get going, you need a good host. And in this case, that host is iodine. A little bit of iodine acts as a catalyst. It's like a molecular matchmaker. It skillfully brings everyone together, makes the reaction happen way faster and more efficiently, and then it just steps aside at the end, totally unchanged.
And the result of this new recipe? Wow. This number really says it all. After tweaking things just right, the researchers hit an 82% yield. Now, for those of us who aren't synthetic chemists, that is a fantastic result. It's a huge sign that this process is super efficient and actually practical.
So how in the world does this actually happen? Let's zoom in and follow the atoms as they perform this carefully choreographed molecular dance, rearranging themselves to snap into that final perfect thiophene ring.
Okay, the dance begins as that iodine catalyst gets to work. It helps one of our starting molecules, the ketone, get into a much more reactive form called an enamine. That's molecule I you see there. Meanwhile, our other starting material, the alkene, gets prepped for action as block I. The stage is set.
And here comes the crucial first move. Intermediate 2 attacks intermediate 1 and bam! They form a brand new carbon-carbon bond. This is the moment our two building blocks get linked together into a longer chain, which we're calling molecule 3. The basic skeleton of our final product is starting to take shape. Now, it's time for the star of the show. That elemental sulfur we added at the beginning finally makes its grand entrance. It swoops in and inserts itself right into the chain, creating our new intermediate, IV. You can see that sulfur atom right in there, poised and ready for the grand finale.
And this is where the real magic happens. That long chain we just built, molecule IV, does something amazing. It folds back on itself. The sulfur atom at one end reaches out and attacks a carbon atom further down the line. It's a process called intramolecular cyclization, and it literally snaps the chain shut into a ring, forming intermediate V.
And for the final act, a little helper molecule gets kicked out, the bonds do a final shuffle, and there it is. The stable, 5-membered thiophene ring is born. Our final product, labeled 3, is complete. This is it. The elegant, one-pot transformation we were hoping for. From 3 simple pieces into one complex, super valuable molecule.
But wait, because making the molecule is only half the story. What makes this discovery so cool are the really surprising properties these brand new thiophenes have. Turns out, they don't just exist, they glow.
This is where things get really, really interesting. See, most molecules that glow stop glowing when you pack them together into a solid. It's a problem called aggregation-caused quenching. But as the researchers point out right here, these new thiophenes are different. They actually glow brilliantly, even when they're just a solid powder. That's a huge deal.
And here's the proof, plain as day. On the left, you've got the data, a graph showing a strong spike of light being emitted right in the blue-green part of the spectrum. But on the right, well, that's what the data actually looks like. It's vials of these new compounds just glowing intensely under a UV light. It's chemistry that is literally brilliant.
And it gets even cooler than that. Look at this. The color of the glow changes. This is the exact same molecule, but depending on what solvent you dissolve it in, it glows a different color. This awesome property is called solvatochromism, and it's super useful. It suggests these molecules could be used to build incredibly sensitive chemical sensors.
And here's the kicker. This isn't just some neat trick that works on a microscopic scale. The researchers proved that their method works on the gram scale, still pulling in an excellent 78% yield. That proves this whole process is robust and ready for the real world. It's not just a lab curiosity, you can actually make this stuff.
So, let's step back. What's the big picture here? Well, this research basically hands chemists a powerful new tool. It opens up a super efficient way to build advanced materials for things like next-gen electronics, think even better OLED screens, and it gives us a much simpler way to create the glowing molecules we need for new medical sensors and biological markers.
Ultimately, this is just a perfect example of how discovering one single elegant chemical reaction can unlock a whole universe of new materials with amazing properties. It really makes you wonder, now that we have this recipe for making things glow, what other incredible things could we build with it?